Hi, my name is Harlan. Welcome to the Machacon Mechanical Engineering channel. Our topic for today is undamped free translational vibration of 1 degree of freedom systems. Supposing a system can be modeled as an object having a mass of m suspended on a spring with a stiffness k kilonewtons per meter, and this object is pulled downward from equilibrium point by x sub o meters and by an external force, and it is suddenly released and left to vibrate on its own. Determine the natural frequency, the amplitude, the maximum velocity of vibration, and root mean square velocity. So it can be having a diagram as this one, which is K, this is the stiffness of the spring, and then this mass, and it moves by X for the displacement. And on the free body diagram, you can see the restoring force of the spring, K times X, the distance here, and the downward force m times acceleration, or m times the second derivative of x with respect to time. The governing differential equations can be obtained using two methods: the free body diagram and also the conservation of energy method. So using the free body diagram method to obtain the governing differential equation, the object is pulled to a distance of x sub o meters below the equilibrium position and then released. The spring tends to pull up the object back to equilibrium position, exerting a restoring force proportional to the displacement x. And this phenomenon is called simple harmonic motion. And it is opposite to the direction of displacement. Hence, we apply the Hooke's law. F is equal to minus k times x. And applying the Newton's law of motion, F equals mass times acceleration. And so you equate the two values, negative kx, m is equal to m times second derivative of x with respect to time. And thus from this you can obtain the governing differential of equation, m second derivative of x with respect to time plus k times x is equal to 0. The governing differential equation is a homogeneous second order linear differential equation. And using the principle of conservation of energy to determine the governing differential equation, it is this method. Assume the vibrating system with negligible friction and damping, and the law of conservation of energy applies. Hence, the total energy of the system remains constant along the vibration cycle in simple harmonic motion. And this energy consists of two forms. The first one is the potential energy caused by the distortion of the spring, and the second one is the kinetic energy due to the velocity of the mass. At equilibrium position, the kinetic energy is at maximum, but its potential energy is 0. And on the other hand, at the maximum displacement, the kinetic energy is 0, while the potential energy is at its maximum. So the energy equation is this. Kinetic energy plus potential energy is always constant. So taking the derivatives, differential of kinetic energy plus potential energy, and so you get the derivatives of this, and it will result in the same governing differential equation as what we hope obtained in the free body diagram method. The general solution to this governing differential equation is x, the displacement, is equal to b1 cosine the square root of k, the stiffness, over the mass times t, time t, plus b sub 2 sine square root of k over m times time t. And these b1 and b2 are arbitrary constants, where this expression square root of k over m is equal to omega sub n, which is the natural circular frequency or angular frequency, which is equal to 2 pi f sub n. And solving for f sub n, we have here 1 over 2 pi times the square root of k over m. As I've said, w sub n is angular frequency in radians per second, and f sub n is a natural frequency in cycles per second or hertz. So from the general equation below, we determine the constants, arbitrary constants b1 and b2 using the initial conditions. So from here, at time equals 0, x equals x sub 0. So it shows b sub 1 is equal to x sub 0. So you already have the value of b sub 1 based on the initial condition at time t equals 0. And here, so you can directly substitute x sub 0 for b1, and you only have one arbitrary constant left, which is b sub 2. And taking the first derivative of the displacement with respect to time, which is the velocity, you have this expression here, and it shows one arbitrary constant b sub 2. So you can easily solve the value of b sub 2 by substituting the initial conditions of velocity and time. So at t equals 0, v is equal to v sub 0, the initial velocity of the setup. So you substitute these values, and then so you can solve for the arbitrary constant. V sub 2 is equal to v sub o times the square root of m over k. Hence, the displacement can be expressed in this form, now without the arbitrary constant. So as x sub o cosine square root of k over mt plus v sub o square root of m over k sine of square root of k over m times t. And to solve for the amplitude of vibration, we consider the two vectors, this one here and this one. They are 90 degrees out of phase. So b1, which is x sub o, b2 is just v sub o square root m over k, and using the Pythagorean theorem, we can solve for the amplitude with the values of b1 and b2. So this one will be now the expression of the amplitude. So it is clear here, the first vector b1, and b1 cosine omega t. So it's this angle from here to here, which is the same as from here to here. It's just 90 degrees out of phase, and b2 sine omega t is this one, this value, and the resultant will be the amplitude here. Okay, and it can be obtained by using Pythagorean theorem, because you have b1, which is this, and b2. And the natural frequency is this value, which you have solved earlier, and the velocity will be expressed here now. So from the velocity equation. And the maximum velocity can be determined. Vmax, same, Pythagorean theorem, v sub o square root of v sub o squared plus quantity negative x sub 0 square root of k over m quantity squared. And the root mean square velocity is simply 1 over the square root of 2 over this value, v sub max, maximum velocity. And supposing the mass is 50 kilograms and the stiffness of the spring is 8 kilonewtons per meter, and the initial displacement at time equals 0 is 0.1 meters. Okay, so as shown here, the values, and we have this free body diagram, mass 50 kilograms, and this one is the acceleration, which is the second derivative of the displacement with respect to time, and 8 kilonewtons over m per meter, and times the value of x here. And we have solving for the natural frequency gives us from this equation that we have solved earlier, we simply substitute the values, and we will have a value of 2.013 cycles per second, or hertz. And solving for the amplitude from this equation which we have obtained earlier, and we simply substitute the values, x of 0.1 meters and 0 meters per second for the initial velocity is 0, and 8,000 newtons per meter and 50 kilograms of mass, and the amplitude will be 0.1 meter. And the maximum velocity, substituting the values here, we have 0 meters per second quantity squared, and 0.1 meter, and then 8,000 newtons per meter and 50 kilograms quantity squared. We will have a maximum velocity of 1.265 meters per second, or 1,265 millimeters per second. And the root mean square velocity from this equation, RMS, VRMS is equal to 1 over square root of 2 times V sub max, or the maximum velocity. Substituting the value 1.265, you have 0.894 meters per second, or 894 millimeters per second. The displacement equation then coming from here can be simplified to x 0.1 cosine square root of 160 t by simple substitution. And since v sub o is 0, then we can remove this the second term of the equation. And also the velocity equation here, coming from here, and you substitute the values. Remember that v sub 0 is 0, so you can remove this expression, and simply you substitute the values here, and it simplifies to v sub v is equal to negative 1.265 times the sine of quantity square root of 160 times time. So if we graph this here, the displacement equation, simplified displacement equation from here, this one, graph this, the one in blue, okay, and the velocity coming from this one, you graph it, and for different values of time, it will show these sinusoidal curves. And you will notice that when the velocity is maximum, the displacement is 0. Okay? So if the displacement is maximum, the velocity is also 0. That's what we have mentioned earlier. So they are 90 degrees out of phase. So, question: how does increasing the mass affect the natural frequency of vibration? Let us therefore repeat the calculations using various values of mass: 60 kilograms, 70, 80, 90, and 100, maintaining the same spring stiffness of 8 kilonewtons per meter, and then graph the results. And you will see this, that as you increase the mass, the frequency in hertz lowers, reduces. Why are we doing this? Why am I asking this question? It is because It is important when you tune the system for the right frequency. Remember, the natural frequency of the system has to be tuned so that it will not be the same as the forcing frequency that is causing the vibration, so that resonant vibration can be avoided. Okay, so you have to tune it. So you can tune it by either increasing the mass or changing the stiffness of the spring. So you will now see a relationship of the mass of the frequency with respect to the change in mass. How does increasing the spring constant or the spring stiffness affect the vibration frequency? We repeat the calculations using different values of spring stiffness: 10 kilonewtons per meter, 12, 14, 16, and 18, and maintaining the same mass of m equals 50 kilograms, and then we graph the results as follows for different values of spring stiffness in kilonewtons per meter, and you have the frequency in hertz. Note that as you increase the stiffness of the spring, and you will see that the frequency also increases. So you will see a relationship, and it is important when designing a vibration control system for your equipment. You need to visualize it in your head, the relationship between vibration frequency, natural frequency, and the mass, and also the relationship of the natural frequency with respect to the stiffness of the spring. How does increasing the mass affect the root mean square velocity of vibration? Let us repeat the calculations for various values of mass: 60, 70, 80, 90, and 100. And maintaining the same spring stiffness of 8 kilonewtons per meter. And we graph the results here. As we can see, as we increase the mass, the maximum, the root mean square velocity in millimeters per second also reduces. So if you want to reduce the velocity of vibration, you increase the mass. How about the spring constant or the stiffness? How does it affect the root mean square velocity of vibration? Try plotting in results for K equals 10 kilonewtons per meter, 12, 14, 16, and 18, maintaining the mass of 50 kilograms. And then graph the results, and you will see that increasing the stiffness of the spring or replacing the spring with higher stiffness will also result in a higher root mean square velocity. It varies from a little more than 800 until a little less than 1,400 millimeters per second. Okay, and this is about free vibrations which are undamped of 1 degree of freedom systems. And thank you for watching, and I would like you to stay tuned for more video tutorials on mechanical vibrations. Please stay tuned to Machacon Mechanical Engineering channel. Thank you.